we are going to use now not just one capacitor or inductor, but we are going to use a, going to have our ZL here, and then oh, by the way, there's other variations of this capacitor inductor kind of a thing, right? We could put the inductor in parallel, or we can put the capacitor in series, right? But why do you think we're not even looking at these variations? And of course, we would just be able to match ZLs that are here or here. But why are we not even looking at those variations? What do you think? It's kind of, no, it's a little bit of, if you have some, if you've been looking at circuits a lot and a particularly active circuits, then you know that a lot of them will require biasing. So for example, when you have a transistor, you're going to need to let in DC current. And both of these circuits, if you notice, allow DC currents to go in to ZL, right? The inductor is a short at DC, and the capacitor presents an open in shunt. But then if you have an inductor that's in shunt, it's just going to short out the DC, and then the capacitor is going to prevent the DC from coming in. It'll open it. So this is why those aren't practical, basically, while these are practical matching networks. Okay, now so the third one is you have ZL, and then you have a series inductor, and then you have a shunt capacitor. Okay. And now you want to bring ZL to Z0. So let's think about this one. What do you guys think in terms of what is the region on the Smith chart? Now you probably are guessing that it's probably a bigger region, right? Because we now have the 2 degrees of freedom here instead of 1 degree of freedom. What do you guys think? Any suggestions how to even approach this problem? What?
Like you can say like Z0 is equals to the parallel of C and L plus ZL to
Okay.
be matched.
Yeah. But it's hard to see unless you see it where in the Smith chart ZL should be in order for that parallel combination to give you Z0. So the way to think about it is to start again from the output and say, okay, my capacitor here is going to need to finally move me to Z0, right? Okay. And we know that what a capacitor, and so since we're adding a shunt capacitor, we should be on the Y chart, okay? So we know that a shunt capacitor is going to move you this way, right? It's going to add, or clockwise, it's going to add a susceptance, a B. All right? So the impedance, so in other words, the admittance looking into here, let's call this Y1. The admittance Y1 better be on this semicircle here, so that I can just use a capacitor, right, and move it to the center, right? So Y1 better be here, okay? So that's the first step, to recognize that Y1 better be here. Now the second step because I need to go to ZL, I need to then convert Y1 to Z1. So then, and we know how to do that, so that means that Z1 better be here. Okay, that should be my Z1. Okay. So now I know where I have to move my ZL. I need to move my ZL to this semicircle, because then this this impedance, which I'm calling Z1, will become Y1 on the Y chart, and then I can just use a capacitor, a shunt capacitor, to move it to the center. Okay? So now the question is, where should ZL be so that I can use an inductor to bring ZL to Z1, this semicircle? Where should ZL be? Go ahead.
Anywhere for left part
Where would you say the left part is?
from r equal to 1.
From R is equal to, oh, you mean like anywhere here? You mean like if this is the R equals 1 circle,
Yeah.
are you saying outside the R equals 1 circle?
I mean left side but below the red part.
Oh, okay. Okay, so you mean, basic, yes, exactly, okay. So you mean this region that's outside R equals 1, but below that region, that's correct. Because why? Because whenever our ZL is here, then we know that a j omega L is gonna be moving us on a constant R circle. We're gonna be on a constant R circle, and then we're gonna be moving this way, and that's not a very constant R circle, but we're gonna be moving this way until we hit this point. From this point, we're gonna go to the Y chart. We're gonna go here, and then we're gonna find the correct capacitance to get us to the center. And I can do that with any of these points, okay? As long as they are, as John said, below the R equals 1 and below this arc. If they're here, I can't do it, because the inductor is just gonna move me here, and that's not gonna help. So it needs to be here. So the region then is this region here. That region.